sinusoids on T lines with arbitrary load. And so in this case, we're going to talk about what happens on a transmission line with intrinsic impedance Z0 under sinusoidal excitation, length D. Here's my sinusoidal source. And we're going to connect this to an arbitrary complex load, ZL with the squiggle on it. So it'll have an amplitude and a phase. So it's some combination of inductors and capacitors and resistances that I can represent as a Thevenin equivalent load, complex phasor. Now, the first thing to note here is that everything you learned about transmission lines is still valid. If I want to calculate a reflection coefficient, I use the exact same formula we've been using the first 4 weeks of class. That is ZL minus Z0 over ZL plus Z0 is a reflection coefficient. See, if ZL is a real value, it's just like the real valued reflection coefficients that we've had calculated in the past. And this is simply a fact that whatever total load voltage that I have at the terminals of that transmission line and the total current that I have coming out of it must follow Ohm's law and must be continuous across this border. So really, this reflection coefficient, even though it has this odd mathematical form, is just basically saying this is the relationship between the forward and the backward propagating waves in order to satisfy that boundary condition. In the sinusoidal arbitrary case, where I could have any kind of load, my reflection coefficient can be complex. That's the only difference. The same cases of Z sub L is equal to 0, a short circuit will give you a -1 reflection coefficient. Z sub L equals to infinity will give you a plus infinity reflection coefficient. A Z sub L that equals to Z0 will still give you a matched condition with 0 reflection. But now, especially if I have a complex Z sub L, I'll get a complex reflection coefficient. In fact, one of the homework problems that I usually give students is to show that if you've got a purely reactive Z sub L, a capacitor or an inductor, in the absence of resistance, you can show that even though there's a complex number, the magnitude is always 1. So in a way, it's kind of like putting an open circuit or a short circuit on there. An inductor or a capacitor kind of behaves like an open or a short circuit. The phase of the reflected wave changes depending on those 4 different loads, but the result is always the same. All of the voltage, 100% of it, reflects back down the line. And that makes sense, right? Because an open circuit and a short circuit, or a pure capacitor or a pure inductor, none of those things offer the wave or the power being carried by that wave anywhere to go. Unless there's a resistor there that can absorb power, 100% of the voltage is going to have to reflect back. So that's one thing that we'll have to get used to, the fact that now reflection coefficients are going to be complex. And in fact, once you figure out your reflection coefficient, you can calculate your voltage standing wave ratio. Remember, that's equal to the max voltage, total voltage, divided by the min total voltage. When does the max occur? Well, it's when my forward and my reflected wave line up. And when does the min occur? It's when my forward and my reflected wave are out of phase and destructively interfere. That ratio you can show is proportional to this value right here. Vswr is 1 over 1 plus the magnitude of the reflection coefficient divided by 1 minus the reflection coefficient magnitude. So it's interesting that what is the Vswr for a short circuit? Well, I put -1 in there. I take the magnitude, I get 1. 1 plus 1 is 2. 1 minus 1 is 0. Infinity. Just like an open circuit. What happens when I put a complex or a purely reactive load, like an inductor or a capacitor, in the absence of resistance? I just told you that the magnitude of that reflection coefficient is always 1. The phase changes, but the magnitude is always 1. And that basically means you're going to get 1 plus 1 over 1 minus 1. Again, Vswr is infinity. I'm reflecting all the signal back. Any other kind of load, though, is going to give you a Vswr less than infinity. Greater than 1, but less than infinity. And you can calculate it with this thing. There's one more important formula that I want to put on the board, and I think we'll break after that because we'll be ready to work an example on how to incorporate this into your analysis. But this is the most important. And this is the Thevenin equivalent impedance as seen at the front of a line of length d for this type of system where you have an arbitrary load and a transmission line of impedance Z0. And here's the nasty expression. This is equal to Z0 times the quantity. In the numerator, I have ZL plus J Z0 tangent beta D. And then in the denominator, I have Z0 plus J ZL tangent beta D. So unless you have an expensive calculator, this is a little bit tedious because there's a lot of complex math. It's a nasty kind of expression. But it turns out that this key result here has sort of the same properties that we learned in our simpler open circuit and short circuit cases. It repeats itself every half a wavelength. So every time you get to a half a wavelength multiple of a transmission line length, you'll get the same Thevenin equivalent impedance. Why? Because tangent repeats itself every 180 degrees, which corresponds to half a wavelength on a transmission line. And it's interesting that, you'll start off with a complex load, and sure enough, if you put in d equals to 0, the tangents drop out, the Z-naughts cancel, and you're left with the Thevenin equivalence of Z sub L. That's a good sanity check. So you start out at the complex load, and as you move away from it, it will change both its real and imaginary components. In fact, it will do the same crossover effect as well. At some points, it will look like an inductive load. In other points, it will look like a capacitive load, regardless of what you actually started out with. So what we'll do when we come back next time is we'll work an example from power. We'll give you power engineers some love and show how do you use sinusoidal transmission line theory to figure out what the city of Greenville looks like at the end of your substation, from your substation's point of view several hundred miles away, or from your generator side. And we'll solve for currents and high voltages. Okay, see you on Tuesday for my first trick of today. Well, yeah, okay, this is how we're going to start class. I've got a couple things I want to pass around to kind of illustrate some of the things that we've been talking about with regards to sinusoids on transmission lines. If we could summarize what we've learned about that in a nutshell, it's that you need phasors to describe sinusoids on transmission lines because it's a really complicated function of space and time if you don't use the phasor transform. Forward and backward propagating waves travel at travel at the same frequency, but with different phase tapers. One is positive, one is negative. As a result, they constructively and destructively interfere at different points along the line, and you get standing waves. You also get something called load transformation, which means what you put at the end of the line, an open circuit, a short circuit, a capacitor, an inductor, a resistor, any complex load, is not exactly what you're going to see depending on what length of the line that you observe the Thevenin equivalent impedance at. And we kind of went over some examples of arbitrary loaded lines. And I'm going to work an example of an arbitrary loaded line here after I do a little bit of show and tell. And the first thing I'm going to do is I'm going to pass out two devices. I'll kind of describe them. Phenomenal. In fact, maybe what I can do here is get the overhead camera going so that those at home can get a close-up look of the things that I'm going to pass around. Perfect. Okay, so what is this thing here? This is actually two identical devices on the same printed circuit board. In theory, you could just saw this thing in half and you'd have two of these. Does anybody know what this is? Strange alien technology. Yes, it's an antenna. What kind of antenna? Patch antenna. A patch array. It's actually four patches tied together so that you get a different pattern. You get a really skinny pattern coming right off the top instead of a fat pattern, which is what a single patch would be. And it's interesting, patches are just hunks of metal. This is a printed circuit board. You see, you got ground plane on this side, hunk of metal here, fed by a transmission line to another hunk of metal fed by a transmission line, and so forth. And this is like the central feed point. So your signal would go into here, it would split off, it would go into here, and propagate up here and excite these patches. Now, patches look kind of like like if you were just to feed the patch like that and you design this properly, this would look effectively like a purely real load at the end of the transmission line, ideally. And it's not a resistor. That load, what that load physically represents in the circuit model, is voltage and current going down, striking the end of the line, dumping into a circuit resistance, which is really radiated modes of power. It's sending power out. It's not ohmic losses, which is what a lot of your low-frequency resistors in a circuit model represent. So we have a transmission line. This is 50 ohm line, terminated in a resistance here. And actually, it's a complicated network of these radiating structures. And as a result, what you design is not necessarily what you get. You try to design something, and the reality never quite matches up with your simulated design software for this patch antenna. Maybe impedance is an imaginary value, or the trace widths when you went to implement them on a printed circuit board, the fiberglass wasn't quite epsilon r equal to 4.0, or was inhomogeneous, or something like that. And so the students that did this put a little clever backdoor for helping tune their circuit. This is called a stub line. You see, it's a parallel fan-out line of a certain length, and it terminates into nothing. Now, in open circuit, as you move along, the center frequency of this thing looks to be about 2.45 gigahertz. So it'd be like Wi-Fi radiators. As you move along, this stub looks to be probably in medium, a quarter wavelength or less at that frequency. And what you'd find is that it started as an open circuit, but as you looked closer and closer along the terminal, it would be a smaller and smaller negative J something value, a capacitor. In fact, when we do microwave design lab, it was a PhD level class here at Georgia Tech, where students actually build a lot of these devices, and they have to tune them and match them. They'll put stubs, and I like to call them desperation stubs. It says they don't know exactly how much they're going to have to tune out, so they just throw a long stub there. And then they put it on the network analyzer, see how well it's radiating, how well it's matched, and then they take like an X-Acto knife and scrape away, desperately, the length of the stub until it's tuned perfectly. Being careful not to scrape away too much, because you can't go back, right? So, yeah, Lam, you have a question?
You send signal out.
That's right.
Okay.
They both transmit and receive. There's something really interesting in electromagnetics called the reciprocity theorem, which says that you can put a voltage waveform here and they radiate with a certain pattern. Or you could put a voltmeter at the end of the line and signals will experience that same absorption pattern as they come in and excite a voltage at the terminal of the antenna. So either one, an antenna can always be used as a transmitter and a receiver. So here, I'll go ahead and pass this one around and start taking a look at that. And one more device for show and tell. Here's a single patch. And let's see. I've got a patch antenna here. And you'll see a little transmission line. Yes?
One question about that. Where would you use something like that? Like that size?
Of that size, that would not be a consumer electronic device. That was some special measurement we were taking that needed directional antennas. You're not trying to cover an area. You're trying to focus a beam with some gain in a particular area. You don't usually put those on like mobile devices or Blackberries or things. Yeah, it was a research tool. I can't even remember what it was used for. We've got so many spare part senior design projects and research project cast-offs in my room. I've got a big box full of them, and whenever I need something for show and tell, I just reach in there and bring it down here. I thought, oh, a stub. That's good. We know what stubs are in 3025. That was the criterion for picking that particular antenna out. I forget the story attached with it. I do remember the story attached to this one, though. This was a project that we did a couple years ago for a power equipment manufacturer. They make protection equipment for substations, high voltage substations. So every once in a while, substations blow up, it turns out. And so, and the problem is they'll just burn and burn and burn, and they just look like a resistive load at the end of the line to the power company. So you can't tell when to shut it off. And so this guy right here is part of a sensor that you put on a high voltage line to measure current and seeing if you're getting a surge of current that would indicate a fault or a failed piece of equipment in the substation. And that way you can throw the switch and make sure nobody gets hurt or none of the equipment gets hurt. So this guy's just a little patch antenna. You'll see he's smaller than that other patch antenna I move around. What does that mean if it's smaller? Higher frequency. Everything electromagnetic scales with frequency. This is about, I'd say about 2.5 times smaller along this dimension than that comparable patch antenna. That probably means that the frequency is 2.5 times larger. And guess what? This works at 5.8 gigahertz. That's at 2.4. So see, all the math works out fine. And this guy, the reason why I brought this guy down is because he operates a lot like an RFID circuit. He doesn't have a transmitter on the back. This is supposed to be a low-powered device that you just sort of sip a little bit of scavenged energy, either some magnetic energy off the line or some RF harvested energy in certain variants. And all this guy does is measure the line voltage with a very low-powered microcontroller, digitizes it. And you see this little gold switch here? That's a load modulator that just switches between open and short, +1 reflection coefficient, -1 reflection coefficient. And it uses that modulated backscatter to send the information back to an illuminator unit on the ground. And this way you don't have anything, you don't have any people or any stuff in the insulation gap of a high voltage line, because you can't put anything there. No metal, no dielectric, even air. We kind of wish we could evacuate it because air is a lousy insulator, it turns out. But we can at least put some space between there because air is free. And it has to be very low power because nobody wants to change batteries on a high voltage line. Spec is that this thing has to last for 50 years in the field without a drop of maintenance. So I'll go ahead and pass this around so you can see the antenna, and the little gold switch at the backside is the load modulator, just like we discussed in class last period. Any questions about that so far? Okay, let me go ahead now and do a little animation. We did animations for time domain transmission lines. Let's see if we can get something going here for the sinusoidal. Always good to get some visualizations going because we're talking about voltages and currents that are functions of space and time. And in the end, it's just good to see an animation, something that's a function of time, in order to get it up here. Phasors don't necessarily cut it. They didn't for me when I was a student. So I don't expect you to be immediately enthralled and have perfect understanding when you look at one of my complex squiggle variables. Okay. So what do we got here? We've got, let's see. Oh, there we go. Good, good. So let's look at a matched transmission line. Sorry for this being a little bit low. Let me see if I can raise this up so the people at the back can see without standing up. Okay, so what I have here is my standard transmission line, an arbitrary load, a matched source. And this is demonstrating the forward propagating sinusoidal wave and the backward propagating wave, depending on what the load is, and what the sum of those two is. What you would observe if you took an oscilloscope or a voltmeter and put it down the line. Now, this first case is kind of the trivial case, where you have a perfect match. So in this case, 50 ohm transmission line, 50 ohm load. You'll see this green wave, this is the forward traveling wave. The red wave is the backwards traveling wave, but it's zero because it's a match. And so the sum is this black wave, and the envelope is the magnitude of the displacement at any given point on the transmission line, when it sort of like stops erasing the total voltage and just looks at all of the displacements as a function of time. That traces out the envelope, and you can see that max values, which you see at the very end. So here, trace out the envelope. Oh, look at that. That's a nice thing about a matched line. The amplitude is always the same no matter where you measure on the line. The phase is different, but the amplitude is always the same. And that's why we say that the Vswr is 1, or 0 dB, the minimum possible value. Vmax is equal to Vmin, no matter where you measure. The trivial case. Okay. Now, what happens if you have a short circuit? This is a case that we studied. Forward wave goes back. The backwards propagating wave is this red dotted waveform, and the sum is a standing wave. What is the envelope of the standing wave as a function of space? It is not constant on the line. It's actually those humps where you get peaks that are half a wavelength apart and peaks and nulls that are quarter wavelength apart. Let's take a look at that again. So this is total voltage on the line, the black waveform, and the envelope right there, that blue waveform. You see, consistent with a short circuit, it goes to a minimum 0 at the end of the line. And it's only when you start moving away from that does it start to look like an inductor, then an open, then a capacitor, and etc. Not surprisingly, the open circuit looks very similar, except the peak is at the end. There's the backwards propagating wave. Notice it's the exact same amplitude as the forward propagating wave because there's no place for it to go. And you get a standing wave, which is exactly what you did in that physics experiment when your high school teacher took a piece of string, held it taut, and then wiggled it up and down. The wave went down. The mechanical wave went down, reflected back with magnitude 1 reflection coefficient, and made that same standing wave pattern so that there were nulls at certain points of space and peaks at other points of space. Has anybody seen that demonstration done in your physics class? Raise your hand. Oh, good, good, good. We still have high school physics teachers that are following the textbook when they teach waves.
So the peak would be, I guess, 2?
If That's right. If you normalize these two, if these are each 1 volt wave apiece, the forward and the backward propagating wave, then the peak would be 2. And the null would be 0. Yeah. Okay. Let's see. What about a slight mismatch? This would be, in this case, we've got a 60 ohm load, very small reflection coefficient. And you see, that's still enough to make a visible voltage standing wave ratio. There's a wiggling total voltage, and the envelope has a Vswr. See, Vmax is a little bit more than Vmin. It'll be like a 1.2 type Vswr, something around there. Let's see, what about an inductor? What do you think that does? Forward propagating wave, backward propagating wave of the same magnitude, just like the open and the short. Makes sense. If there's a pure inductor at the end and no resistance, there's no place for the power to go, so it's all got to reflect back. But you'll notice it's neither at the peak or at the short. It's something in between at the very end. The voltage and the current at the end of the line are not perfectly in phase or out of phase. It should be 90 degrees out of phase, right? Because it's an inductor. Let's see. See a big mismatch. This is a 250 ohm load. You see the reflection coefficient produces a backward propagating wave that's maybe 2/3 the value. And there we get a nice big voltage standing wave ratio. Not quite infinity, but 5 or 6 probably. That's what it visually looks like. It's always good to not, well, almost always you are trying to minimize VSWR because it represents reflected power. If you've got an amplifier here and an antenna over here on the load side, you want your power to all go to the antenna and radiate out. If you've got a significant amount reflected back, that means a couple of bad things. First of all, you're wasting power, obviously. Secondly, it's not just a waste of power to produce a big signal that you're not using. You're also losing quite a bit on the communication link. You'll be losing signal-to-noise ratio or signal-to-interference at your receiver, and you may destroy communications inadvertently. Thirdly, if this is a high-power application, there are some electronic amplifiers and sensitive components that could be damaged if you send too much power in the wrong direction towards them. So both of these are bad cases, or all of those are bad reasons. Now, here's a complex load. Remember what we said last class period. Complex loads aren't any different than resistive loads. It means that the reflection coefficient is going to be a complex number, but everything else is the same. It makes a standing wave ratio. And you can see that's probably a VSWR of 2. This is a 50 plus J50 voltage standing wave ratio. Or load. Okay. Let's talk about a little bit of loss. Let's do this one first. This is what we're going to talk about at the end of today, but I'll go ahead and introduce it to you. This is a concept of a lossy line. This is matched, but there are some losses, and we'll talk about where the physical losses come from on a transmission line like this. You see, what we really have is exponential decay, graceful exponential decay of the amplitude on the line. When you work through the math of the physics, that's what jumps out of a transmission line equation. You get exponential attenuation of the amplitude. And the envelope is a gracefully decaying exponential. Now, technically, you can also have loss with a mismatch. Let me go ahead and show you what that looks like. So here I've got an open circuit at the end of the line, which means it's going to reflect all the energy. But of course, by the time my signal reflects all the way back here, it's at a lower amplitude than what I started with. As you get kind of a weird line. Voltage standing wave ratio is kind of like a function of position at that point. You get a big Vswr at the end of the line, and then a real minor one at the beginning of the line. And you're heating up your cable in the process. Let's see, here's a high loss line. Open circuited, but Z0 of 67 plus J30. So it's mismatched, but also notice that it's complex. We'll see by the end of class, hopefully, that complex lines also indicate that there is loss on that line. We'll explain why. Yeah, there it is. Very sharply attenuating exponential in the total envelope. So when you look at the total envelope, there it is. It looks like a very sharp exponential with a little bit of ripple at the end. But one nice thing about high loss lines, you don't usually have to worry about Vswr on them because the signal dies out too fast. Now, in our class, in our study, we're mostly concerned with low loss lines. If they get really high loss, then they're not particularly useful anyway, so we don't have to worry about them. And we'll go over that as a little precursor. Now, all these videos are up on the website if you want to click through them and look at them in closer detail. I know some of the people in the back might not be able to see them as well, or the video students, but this is all available on the net if you want to take a look at that. Any questions? Perfect understanding? Then it's time to do a problem. Okay, so our first example here is going to come from the power industry. We'll give some power engineers some love. Let's say I had a power plant. We'll make a nuclear power plant. This is the cooling tower, by the way. Do we have any nuclear engineers here? No, they don't have to take EMAG anymore? Sometimes I get nuclear engineers in my class. They still do? You just scared them all off? You ganged up on them? You double E and Comp students? Okay. Well, we'll still do the nuclear engineering example. I was very embarrassed though one day. When the first time I did this, I said, "Oh yeah, and you got some nuclear stuff here." And they said, "That's the cooling tower, Professor Durgan. You don't know anything about nuclear engineering." And it's true. But I do know how to model this with transmission line. I do claim to know how to do that. So here's our generator, cooling tower. Here's a reactor, and somewhere here's this generator building. And let's see. Here's a high voltage tower. And we got usually 3 phases of transmission line, because that turns out to be a great way to transmit power. Each of these looks like a transmission line independently, so we'll assume that we're just going to analyze one phase. And of course, before you get to this point, there's a step-up transformer. Let's say we've got a little power plant, and our step-up transformer is going to make this whole thing look like a 120 kilovolt source. Actually, a lot of sources, once they're put on high voltage line, and depending on how far you're going, can step up to 500,000 volts or even 1,000,000 volts. Why do they set the voltage up so high? Yeah?
Because so we don't have to have a lot of current.
That's right. Remember, the product on a transmission line, product of voltage and current, is always watts. That's the amount of power that you're transmitting. So, generator generates a certain amount of voltage and current, certain amount of power. You want to distribute the voltage and current in such a way so that voltage is maximized and current is minimized. As we'll learn again, as I say, in the lossy section of the transmission line unit, your principal losses in this particular kind of transmission line network is from conductive losses on your cable. I squared R losses. I squared R losses. If you double the current, you quadruple the loss. If you halve the current, you cut the losses by 25%. So that's why you want as little current as possible and as much voltage as possible. Of course, the voltage means that you're going to have to get your lines really high off the ground, and you have all these other issues like arcs and other things to contend with, insulation gaps. But that's a fine trade-off to get 99% or whatever the efficiency is of the transmission grid these days. So shuttling electronic power around on the transmission grid is an extraordinarily efficient way to move power. It is, we wish the other parts of the network behave with that degree of efficiency. It's like 98, 99%. We wish the Carnot cycle at the coal-fired plant was greater than 30 or 40%, whatever it is, when you build those kind of plants. Once you get something into the electrical domain, it's remarkably efficient. You just can't store it. That's the problem. The fundamental problem of power engineering. We wish we could hold on to it. So then, you go on this transmission line that's very high impedance, so that you're carrying lots of voltage, little current. And then you step down to a load, which could be a neighborhood or a city. So let's see. This guy I'm just going to model him as a 120 kilovolt source. I've got a transmission line. And what does the city look like? Well, for our intents and purposes, for our little modeling exercise, it's going to be 10 kiloohms. A 10 kilo ohm resistor. That's what a city looks like to the power company, a resistor that you can charge money for. And we'll say that our intrinsic impedance of this transmission line is 12K. Let's see, what else can we do? Oh yeah, we'll say that this is several hundred miles, such that at 60 hertz in medium on the transmission line, the distance, the electrical distance, is about 1/8 of a wavelength. And of course, we're going to have an input current and voltage that we're going to have to solve for, and an output current. And if this were an electromagnetically insignificant transmission line, this would be a trivial problem to solve. There would be no load transformation effects, and you just have 120 kilovolts across a 10 kilo ohm resistor. That's, of course, not the case. Instead, I'll show you how to solve for all of the quantities on this transmission line through a simple 6-step program. If you do not follow the 6-step program, you'll be overwhelmed by the complexity of the problem, and you'll have to enter into a 12-step program. Okay? So follow carefully, because this is how you do your last homework problem. Step 1. Load transformation. Characterize my input impedance, Z sub in, or the Thevenin equivalent input impedance, what we called last time. Well, for that I'm going to have to use my load transformation equation. Z in, we said, is equal to Z naught times the quantity of my load impedance, complex load impedance, plus J Z naught tangent beta D, Z naught plus J ZL, load impedance, tangent beta D again, all multiplied by the intrinsic impedance of the line. Now, of course, beta D, in our example, beta is always 2 pi over lambda. And I told you that the distance, the electrical distance, was really lambda over 8. Which means lambdas cancel. 2 cancels with part of 8. 4. And what I get is pi over 4. 45 degrees, right? If you're reporting the number to your boss. If you're going to do calculations, you keep it pi over 4. Okay, so then when I plug in everything, I get 12,000 times 10,000 plus J, 12,000 tangent pi over 4 over 12,000 plus J, 10,000 tangent pi over 4. And let me put this in the magic professor calculator where everything is calculated ahead of time.
That should be another 0 there.
Is it a 0?
The first Z naught.
Oh, yeah. Thank you. Oh, that changes everything. Let me redo the calculation. Oh, yeah. Look, this is basically 12 kiloohms at an angle of 10 degrees. Or if I write this out in Cartesian, real and imaginary complex components, it's 11.8 plus J 2.2 kiloohms. So interestingly, this transformed our real load into a slightly inductive load. We started out with a real resistance, and now we've got a significant amount of reactance, plus J 2.2 kiloohms. And that's going to affect our transmission of power. The mismatch will cause a slight Vswr, which is important when you're transmitting hundreds of thousands of volts. Right? You don't have quite the same level of tolerance of deviation in that kind of network than you do on your printed circuit boards and things. Where you can say, 10, 20% deviation from my expected value, not a problem. Well, here you're talking about 100 kilovolts. So power industry is much more sensitive to transmission line effects in the relative sense. Okay, so that's our first step. Now let's do step 2. Step 2 is solve for your source side input voltage and current. We now have enough to do that because what we've said is we've got this 120 kilovolt source. And it is now connected to a transmission line whose Thevenin equivalent impedance, Z sub L, was just calculated to be 11.8 plus J 2.2 kiloohms. And this becomes a simple Ohm's law problem. We already know what Vin is. I didn't put a source resistance in this problem. In reality, there would be a source resistor here, but I'm trying to take it easy on the math here. Vin, of course, is your source impedance that you've connected directly to the line. 120 kilovolts at an angle of 0 degrees. In you just find, using Ohm's law, 120 kilovolts divided by my 11.8 plus J 2.2 kiloohms. And put that in the calculator, you get 10 at an angle of negative 10 degrees amps. That's how much current is flowing on that line, or at least flowing into the line. Any questions so far? Pretty straightforward up at this point. Yeah?
So when you have a source resistor, would you be able to change it?
Yeah. If I were to give you a problem with the source resistance, this would be a voltage divider across whatever resistance value I gave you here, and whatever load impedance there. ZL over. I should have thrown one in because it's not that hard. But instead I said this was 0. No big deal.
Dr. Gargan?
Oh, yes.
This is Bill in Savannah. In step 1, I thought you were solving for ZN, not ZL.
Oh, you're right. I wrote the wrong thing here. Thank you for that clarification. Board typo. Phew, that was confusing. Now, this is the equivalent input impedance given a ZL that was at the end of the line. Thank you for pointing that out, Bill. Any other questions? Okay. Now, let's go to step 3. Step 3 is kind of the hard part. Step 3 and 4. It's where the rubber meets the road. Step 3 is enforce the source side continuity. So let's go back to the transmission line equations. We said V of Z is going to be equal to some forward propagating wave minus exp to the minus j beta z, a backwards propagating wave exp to the plus j beta z, And our current solution is going to have this form. Okay, so that's our general total form. And what we're going to do in step 3 is set up the formula that allows us to solve for the individual forward and backwards propagating waves on this network. How do we do that? Well, evaluate it at the front of the line. If we're using the convention where z equals to 0 is the front of the line, we could also do that thing where z equals to negative d at the front of the line. In that case, you just put in negative d. It doesn't matter. You can use either convention you want as long as you're consistent. What is it when you put in z equals to 0? Voltage becomes V plus V minus phasor. And we know that because of continuity, those two must add up to 120 kilovolts. Likewise, current evaluated at the front of the line is going to be equal to V plus over Z naught minus a V minus over Z naught. And that is going to have to be equal to 10 at an angle of negative 10 amps. We solved that in the previous step. Well, we know what Z naught is. It's, what was that, 12,000 ohms? Yeah, 12,000 ohms. So we know that. We don't know what V plus is. We don't know what V minus is. But we have two equations, two unknowns. So that's the next step. Solve V plus and V minus. I won't go through all the gory details. The notes are online. But I put this in the Magic Professor calculator, and I get that my V plus is 119.5 at an angle of negative 1 degrees kilovolts. It's almost looking like my source voltage, my full 120 kilovolts at an angle of 0 traveling down to the end of the line. Ah, but there's a reflected wave. That reflected wave, if I calculate it, is 11 kilovolts at an angle of 85 degrees, traveling back this way towards the generator side. So that's 10% of the voltage, almost. A significant amount, and it's quite different in phase as well. So that's step 4. That was easy enough. Step 5. Solve for your load side voltage and current. Well, that's easy enough to do, because all you have to do now that we know our V plus and our V minus, is just evaluate your voltage and your current at the end of the line. Plug in Z equals to D, since we said Z equals to 0 is the front of the line. And what do we get? V plus that we found in the last step, exp to the minus j beta d. Beta d in this case we said was pi over 4, plus V minus exp to the plus j beta d, which we said was pi over 4. And this gives you a load voltage when you calculate it all out of 109 at an angle of 45.2 degrees kilovolts. When you calculate the current, you plug in these exact same numbers for your current expression, the V pluses and the V minuses that you solved in the previous step. Keeping in mind all the while that this is still 12,000 ohms of intrinsic impedance. Remember that transmission lines, high voltage transmission lines, have a very large effective impedance. You've got basically a steel cable usually that's high above the ground plane or return path. That's a very inductive, not a very capacitive system. As a result, you got, when you figure out your impedance, it's the square root of L over C. Square root of very big per unit length inductance over very tiny per unit length capacitance, very large value. And when we compute this, we get 10.9 amps at an angle of 45.7 degrees. And as a sanity check, this is step 6. Verify answer with Ohm's law. This is how you close the loop in your logic. Always an important thing to do. We got this much voltage at the output, this much current as the input. If we set up and do this procedure this way, we can check ourselves. When we get back to the load side, the ratio of our load voltage to our load current should be Z sub L. In this case, Z sub L was a real 10 kiloohms. If we divide 109 kilovolts by 10.9 kiloamps, complex voltage divided by complex load, it's going to be equal to 109 at an angle of 45.2 degrees. We said this when we worked through the calculation was 10.9 at an angle of 45.7 degrees. This is kilovolts, this is amps. 109 divided by kilovolts divided by 10.9 amps is going to be 10 kiloohms. And that angle is going to be 45.2 minus 45.7, or negative 0.5 degrees, which to any engineer is 0 degrees, right?
Yeah, I was going to say, why aren't they exact?
Because Professor Durgan didn't punch in enough digits on his calculator.
Okay.
Any engineer, any self-respecting engineer will treat this as 0.
Okay.
Okay? We're engineers, we're not physicists. We're not trying to calculate physical constants to 7 decimal places or more. That's 0. For very small values of 0. Right? Okay. Any questions so far? Doing good? Perfect understanding? Yeah.
How would we do something like a little test?
How would you do something?
Right?
Yeah, that's right. You would not be able to do something this long and involved on a test. So I might give you a simplified version where you maybe answer some conceptual questions. Like, here's the full wave solution on a transmission line, a voltage and current. Write an expression that would give you the output voltage or the input voltage. Something like that. There are always ways to simplify these problems. That's right. What?
You probably answered that on the upcoming test or the test after that?
That would be an example of a simplified question that I could ask on a test.
On the upcoming test?
That I could ask on any test.
Okay, cool.
Remember, this is being filmed. And this is looking desperate. You guys are going to do fine. Don't worry about it. Okay. And I'll also notice that we work through a solution here, and when we're done with the solution, we've got everything we need to characterize this network. We know what the input voltage is, the input current, the output voltage, the output current. We know what the forward and backward propagating wave. So at this point, I could ask anything you wanted to know. What is the voltage, total voltage on the line, 7/32 of the wavelength down this line, or something like that. You can characterize everything at this point. It took a lot of work to get there, but you see there's a lot of rich behavior going on. Yeah.
You don't really have to worry about reflection coefficients or anything like that when doing this analysis, I guess.
We did it without a reflection coefficients, but that's actually another way to double check your answer. Your V minus should be equal to your load reflection coefficient times V plus. Yeah.
So is the power going into the line going to be the same as power going out of the line?
Yes, so that's a great question. And what you should find in this simplified system that I had, I only had one source that was putting out power. So you can calculate that very easily, right? It's the real value of 1/2 the output voltage times the output current. Complex output voltage times complex output current. You got to take the real part because you don't care about the VARs on the line, or the VARs being supplied to and from, oscillating power to and from the source. And you got to use the 1/2 there, right? Because we're dealing with sinusoids in terms of real-time averaged power. If you average sinusoidal power, it's always 1/2 times the peak amplitudes in that expression. So we know from our basic circuit theory how to calculate the real amount of power leaving the source. We still have, at this point in the class, a lossless transmission line. So despite all the craziness that's going on to and fro on the transmission line, none of that power is being absorbed. It's transporting some to the end of the line, and some is going back to the source. We just figured out how to calculate the net power delivered to the source. That should be equal to the net power delivered to the load. 1/2 the real value of voltage squared divided by impedance, right? Yeah. So that's yet another way to check that you did the problem right. So for example, if you're given a homework assignment where you've got a lossless transmission line and something is being absorbed by the load, you can use some conservation of energy. If somebody asks you to set up a problem that asks you how much power was reduced when that cable was damaged, right? You say, oh, the power into this matched transmission line, the only place it can go is the load before it's damaged. When you damage it, you can make a Thevenin equivalent impedance load for the lossless section of the transmission line after the break point. And any power that goes into that equivalent resistor must be absorbed by the end of the line. So it's a good way to simplify that circuit. If you don't know what I'm talking about, that's probably because you haven't tried the homework yet, right? Yeah. That's okay. You've got hours and hours before that's due. Okay. Any other questions before we get into lossy lines?